The spacecrafts were flying at about 55 kilometers over the surface, and they were able to return the best gravity map ever of any celestial body.
For years, we thought the moon was a dead rock, silent and unchanging. But NASA insiders have uncovered shocking secrets. The moon bends and flexes like it's alive. One side is hotter than the other, and hidden radioactive heat still burns beneath the surface. Strange moonquakes, dangerous gravitational traps, and even buried ice could change everything we thought we knew. What else is the moon hiding right now? Join us. The moon is alive and moving. The moon is not what we thought it was. For decades, we imagined it as a silent, lifeless rock circling Earth, a frozen remnant of the solar system's violent beginnings. But new discoveries have forced scientists to admit something astonishing. The moon is moving, bending, and even breathing in ways no one expected. It is alive in a strange, mechanical way, responding to invisible forces that tug at it constantly. How can a dead rock rise and fall by several feet? Why is one side of the moon hotter and more restless than the other? And what terrifying challenges does this pose for NASA's upcoming missions to send humans back to its surface? What researchers have uncovered is that the moon flexes under Earth's gravity, much like a rubber ball being squeezed in a giant hand. This effect, known as tidal flexing, means the moon's surface doesn't stay fixed in place. Instead, it rises and sinks by several feet over each 27.3-day orbit, creating a subtle but continuous rhythm of expansion and contraction. The idea that the ground beneath your feet on the moon is literally shifting up and down as you stand on it is unsettling. Yet this is not a glitch in measurement or an error in interpretation. Sophisticated instruments, including NASA's Twin Grail spacecraft, measured these changes with microscopic precision and confirmed the moon's surface does not remain still. It is constantly responding to the pull of Earth's gravity, much like the ocean tides here on Earth respond to the moon. Yet this flexing is not uniform across the lunar globe, and this is where the mystery deepens. The side of the moon that always faces us bends and shifts far more than the rugged far side, which remains comparatively stiff and unyielding. Imagine one hemisphere of a world breathing deeply while the other hardly moves at all. This asymmetry is not something scientists expected. If the moon were a simple, uniform body, the tidal forces should affect both hemispheres in a similar way. Instead, the near side appears warmer, softer, and more responsive, while the far side remains colder and more rigid. This lopsided behavior has left researchers scrambling for answers, because it challenges long-held models of how the moon formed and evolved. The explanation they arrived at is as strange as the phenomenon itself. Buried deep beneath the near side is a concentration of radioactive elements, including uranium, thorium, and potassium. These are not scattered evenly throughout the moon, but instead are clustered in specific regions below the surface we can see from Earth. Over billions of years, these elements have decayed and released heat, essentially acting like a hidden nuclear furnace that keeps the near side warmer and more pliable. This radioactive heart explains why volcanic activity once covered the near side with vast dark plains called Maria, while the far side remained untouched. It also explains why the near side still responds so dramatically to Earth's gravitational squeeze. In simple terms, one hemisphere of the moon is still alive with internal heat, while the other has been geologically frozen for billions of years. This discovery means the moon is not a static relic of the past, but a body that is still active in subtle but important ways. Every time it completes its orbit around Earth, the near side flexes more strongly, rising and falling in response to gravitational pull. In a sense, the moon is breathing in space, with each cycle acting as an invisible heartbeat that has continued for billions of years and still pulses today. But how do we know this isn't just an illusion created by overly sensitive instruments? Ryan Park and his team at NASA's Jet Propulsion Laboratory spent years verifying the data, running calculations millions of times, and confirming the results with multiple methods. The precision of the GRAIL mission was extraordinary, capable of detecting gravitational shifts smaller than the width of a human hair. With this level of accuracy, there is no doubt that the Moon's surface moves, and that the difference between its two hemispheres is real. The weirdest part of all is that this isn't just an ancient story of how the Moon formed long ago. It is happening right now, and modern measurements in the year 2025 have revealed the scale of the imbalance more clearly than ever before. Scientists confirmed that the near side's mantle is between 100 and 200 degrees Celsius hotter than the far side's mantle. This is a critical imbalance that shapes how the Moon behaves under stress. The warmer mantle flexes more easily, and that constant flexing generates stress along the crust. These stresses can build up and release as seismic events known as moonquakes, which have already been detected by instruments left behind by Apollo astronauts. Why does this matter for us today? Because humanity is preparing to return to the Moon under NASA's Artemis program, and the discovery of an active, flexing, and asymmetrical Moon changes the game. Gravitational anomalies created by this internal activity can pull spacecraft slightly off course, meaning landers risk missing their targets if these forces are not accounted for. Even more concerning are the moonquakes. If settlements are built in regions where tidal stress is strongest, structures could be shaken or destabilized. Engineers must now plan lunar bases with this in mind, choosing safer regions away from fault zones and designing habitats that can withstand subtle but persistent seismic stress. What was once assumed to be a geologically dead, stable surface is now understood to be dynamic and unpredictable in ways that could threaten astronauts if ignored. NASA's forgotten warnings. The first real clue that the Moon was still alive came from the Apollo program. Between 1969 and 1977, astronauts placed seismometers on the lunar surface, simple devices that measure vibrations and tremors. These instruments recorded thousands of moonquakes, and researchers quickly realized they were not all the same. There were 4 distinct categories: deep moonquakes occurring several hundred kilometers below the surface, shallow quakes happening closer to the crust, thermal quakes caused when the surface expanded and contracted as it heated and cooled, and impact events triggered when asteroids or meteoroids slammed into the Moon. The existence of deep and shallow quakes was shocking, because it suggested the Moon was still releasing internal stress rather than sitting inert. Yet despite this evidence, for decades the scientific community dismissed these quakes as minor anomalies, background noise that did not challenge the prevailing idea of a dead, frozen world. While the Apollo seismometers were revealing an inner life, another mystery was unfolding above the surface. For centuries, humans had only ever seen the near side of the Moon, the familiar face with its recognizable patterns of bright highlands and dark volcanic plains. That changed in the 1960s when spacecraft finally sent back images of the far side. And what scientists saw was like staring at an entirely different planet. Instead of smooth seas of lava rock, the far side was dominated by rugged highlands and dense cratering, almost entirely lacking the volcanic plains that shaped the near side. The contrast was extreme. About 31% of the near side is covered by dark volcanic maria, while the far side has only around 2%. This raised the unsettling question of why one hemisphere had been reshaped by volcanic activity, while the other remained scarred and ancient. Scientists proposed theories, ranging from uneven asteroid bombardment to variations in crust thickness, but none of these explanations really accounted for the sharp divide. The two hemispheres were too different, and the theories felt like patchwork guesses rather than true answers. For decades, the Moon's dual personality remained one of the great mysteries of planetary science. Then, in 2011, NASA launched the GRAIL mission, which changed everything. The mission used two small spacecraft, nicknamed Ebb and Flow, that orbited the Moon for nearly a year, flying in close formation just a few dozen miles above the surface. Their task was to measure the distance between them with extraordinary precision, using microwave signals, detecting even the tiniest changes caused by variations in the Moon's gravity. The precision was staggering. The instruments could pick up shifts smaller than the thickness of a human hair. When one spacecraft passed over a region of slightly denser rock, the increased gravitational pull would accelerate it by an almost undetectable amount, changing the spacing with its twin. By mapping these changes across the entire lunar globe, scientists were able to construct the most detailed gravitational map of any celestial body in the solar system. The results of GRAIL stunned researchers. The Moon was not a solid block of rock with a uniform interior, but a dynamic world that bends, flexes, and responds to Earth's gravitational pull. The data showed the surface rising and falling by several feet every orbit, confirming tidal flexing on a scale never previously measured. Even more astonishing was the realization that this flexing was not happening equally everywhere. The near side shifted dramatically more than the far side, proving once again that the two hemispheres were behaving as if they belonged to separate worlds. For the first time, scientists could see that the Moon's strange asymmetry was not just skin deep, it extended into the interior, shaping the way the whole body responded to stress. So why had scientists failed to connect these clues earlier? Part of the reason lies in how planetary models were built. Traditional theories assumed that bodies like the Moon cooled quickly after formation and developed neat layered structures, a dense metallic core, a mantle of silicate rock, and a solid crust. With no evidence of active volcanoes or ongoing tectonics, the Moon was simply labeled geologically dead. That model worked well enough until the data refused to cooperate. The Apollo seismometers recorded quakes that could not be explained away. The far side looked nothing like the near side, and the GRAIL mission revealed flexing so dramatic it should have been impossible if the Moon were truly inert. Scientists were forced to admit that their neat models were not describing reality. The shocking conclusion, pieced together only recently, is that the Moon is not uniform inside, and that radioactive elements became concentrated on the near side early in its history, providing ongoing heat that still shapes its behavior today. This discovery explains the volcanic maria, the persistent flexing, and the thermal asymmetry that recent measurements in 2025 confirmed to be a difference of 100 to 200 degrees Celsius between the hemispheres. The Moon is, in effect, two very different worlds locked together as one, a chaotic result of a violent birth billions of years ago. So for more than 50 years, the signs were there: moonquakes recorded by Apollo, the alien landscape of the far side, the failed explanations of uneven impacts, and finally the precision of GRAIL. But only now are we beginning to grasp the unsettling truth. The Moon is not dead. It is active, lopsided, and still carrying radioactive heat in its depths, a fact that will shape the way we explore it in the years to come. Cosmic bodies gone mad. If the Moon is still alive, bending and breathing under the pull of Earth's gravity, then the obvious question is what this means for the future of humans living there. Moonquakes, driven by this constant tidal flexing, are not just theoretical concerns, because seismic events have already been detected both by Apollo instruments and more recent orbital studies. Any permanent base built on the lunar surface will face these tremors, and though they may not compare to the devastating earthquakes we experience on Earth, even small repeated shaking could weaken structures over time. Engineers must now factor in not only the freezing temperatures and radiation from space, but also the unsettling reality that the ground beneath them is shifting in ways we are only beginning to understand. At the same time, the very forces that make the Moon dangerous could also make it more hospitable. The concentration of radioactive elements on the near side, which keeps parts of the mantle warmer than expected, might actually provide access to a steady source of geothermal energy. On Earth, geothermal systems draw heat from underground reservoirs, and something similar could theoretically be possible on the Moon if regions of concentrated heating are identified. Instead of being an obstacle, this hidden warmth could help astronauts survive the brutal 2-week lunar night when temperatures plunge to -2 150 degrees Fahrenheit. This internal heating may also influence the distribution of one of the most valuable resources on the Moon, water ice. Permanently shadowed craters near the poles are known to harbor ice, but subtle temperature differences in the subsurface could determine how stable these deposits are and where they are most accessible. In other words, the Moon's inner life might dictate where future colonies can safely build and how easily they can harvest the resources that make survival possible. The Moon, however, is not alone in this strange behavior. Across the solar system, other worlds are revealing similar but equally puzzling dynamics, and when viewed together, a pattern begins to emerge. Take Jupiter's moon Io, for example. Long considered the most volcanically active body in the solar system, it is constantly reshaped by eruptions. For years, scientists thought Io's immense activity was powered by a global underground ocean of magma. Recent gravitational studies from NASA's Juno spacecraft showed that this was wrong. Instead of one continuous ocean, Io appears to contain scattered pockets of magma embedded within otherwise solid rock. The tidal heating from Jupiter's gravity is still enormous, but it does not melt the entire interior. Instead, it creates localized reservoirs of molten material. The parallels with the Moon are clear. Both bodies are being flexed and heated by gravitational forces, yet the internal results are more complex and uneven than expected. Then there is Vesta, a massive asteroid studied by NASA's Dawn mission. Unlike the Moon or Io, Vesta does not display wild asymmetries or volcanic activity. Instead, it is surprisingly uniform from surface to core, showing little sign of the differentiation that scientists expected. Heavy materials like iron should have sunk to form a dense core, but measurements suggested Vesta did not undergo that process in any significant way. The result is an object that is, in a sense, the polar opposite of the Moon, uniform where the Moon is lopsided, stable where the Moon is flexing. Together, these examples reveal that there is no single blueprint for how planetary bodies evolve, but rather a chaotic range of possibilities that defy simple models. Even closer to home, Mars's moon Phobos shows another version of tidal stress at work. Unlike the Moon, which is relatively stable in its orbit, Phobos is slowly spiraling toward Mars, and gravitational forces are literally tearing it apart. Large grooves visible on its surface are thought to be stress fractures, early signs of its eventual destruction as tidal forces overwhelm its structure. In a few tens of millions of years, Phobos may be ripped to pieces, forming a temporary ring around Mars. This is a sobering reminder that the flexing and tearing forces revealed by studies of our Moon are not unique, but universal, shaping worlds across the solar system in ways that range from subtle deformation to complete annihilation. If this much variety exists within our own solar system, what does it mean for the thousands of planets and moons now being discovered around distant stars? One of the biggest implications is for habitability. Scientists often look for exoplanets in the habitable zone, where liquid water could exist on the surface. But if tidal heating is as widespread as the Moon, Io, and Phobos suggest, then worlds outside the traditional habitable zone could still be geologically active and potentially host liquid water beneath their surfaces. Moons orbiting giant planets might have internal heat strong enough to sustain oceans under ice shells, just as we suspect with Europa and Enceladus. The strange, radioactive heart of our own Moon hints that asymmetrical internal structures could be common elsewhere, and that the potential for life is not limited to planets that look like Earth. Habitability may depend as much on unseen forces within as it does on distance from a star. Adding to this picture are the very latest breakthroughs in how we study these bodies. In 2025, researchers proposed using cosmic rays and the so-called Ascarian effect to detect subsurface ice on the Moon. When high-energy cosmic rays strike the lunar soil, they generate particle showers that produce faint radio signals. By detecting and analyzing these signals, scientists believe they can locate ice deposits buried up to 9 meters deep, even if the layer of ice is as thin as 10 centimeters. If proven successful, this method could revolutionize resource mapping, offering a way to pinpoint vital water reserves without the need for drilling. For future Artemis missions and long-term colonization, the ability to locate ice precisely will be a game-changer, because water is essential not only for drinking, but also for producing fuel and oxygen. Taken together, the discoveries of tidal flexing, radioactive heating, and new methods of detecting resources show that the Moon is part of a much larger story. It is not just our closest neighbor, but a laboratory revealing how gravity, heat, and internal structure interact across the universe. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.